Here in binary search tree or BST, we have to compare the value of one node with another, right? So I'm taking some nodes first. So this is binary search tree, or we can call it BST. So suppose some nodes are given 40, 60, 50, 33, 55, and 11. Okay, so the property of binary search tree is if it is a root node, suppose 20 is the root node of that tree, then all the nodes in the left subtree will be smaller than that root node, and in the right subtree, all the node value will be greater than 20. That means here we can't add 25 as a left child of 20. Why? Because 25 is greater than 20. So here in the left subtree, all the nodes should be smaller than 20. So it can be 18 or any other value which is less than 20. Okay, and this is the right subtree of 20. So here the right child of 20 should be greater than 20. So we can take 25 as the right child. That was binary search tree. So when some nodes are given, how we can insert this node in a binary search tree? Suppose initially this tree is empty. That means the first node 40 will be the first node of the binary search tree. So we can add 40 as the root node. Okay, so after adding it now, when we are going to insert a new item, we have to compare it with the root node. So the next node is 60. Now compare it with the root node. 60 is greater than 40, isn't it? So why we can add it? We can add 40 as the right child of 40. So here 60 is the right child of 40. Now the next node is 50. So 50, is it smaller than 40? No, that means we can't add it as a left child of 40. So why we can add it? After comparing the new node 50 with the root node 40, we can see that it's greater than 40. That means it should be added in the right subtree. So here there is another node 60. So can we add it as a left child of 60? Yes, because 50 is smaller than 60. So here 50 will be added in the left subtree of 60. Now the next node is 33. At first compare it with the root node. So the root node value is 40 and 33 is smaller than 40. So we can add it in the left subtree. So 33 is the left child of 40. After that, the next node is 55. At first, that node should be compared to which node? To the root node. So 55 is greater than 40, which means that it will be added in the right subtree. So after comparing it with 40, now compare that node with the right child of 40. The right child of 40 is 60. So is it greater than 60? No. That means it should be added in the left subtree of 60. But 60 already has a left child. That means we can't add it here. So why it should be added? So now the new node is 50. 55 is greater than 50. So it should be added in the right subtree of 50. So 55 is the right child of 50. Now the next node is 11. At first we'll compare it with the root node 40. So 11 is less than 40, then add it in the left subtree. In the left subtree there is a node that is 33. Again compare it with 33. 11 is less than 33, that means can be added as the left child of 33. Okay, so this is a property of binary search tree. That is, any node which is added in the left subtree of a node should be added where? Should be smaller than that root node. And all the nodes in the right subtree of a root node should be greater than that root node. Is it clear what is binary search tree?
Yes, ma'am.
And in our last class, we discussed about the node insertion or node deletion and how we can search this binary search tree, or how we can create the binary search tree from the traversal sequences. So do I need to repeat those things again?
Ma'am, it will be better if you can go through once.
Okay. So I hope you can create a binary search tree when some nodes will be given. Okay, you just have to compare the node with the root node, and then you can decide in which subtree you can add that new node. Okay, so now suppose or here we just added some nodes in this binary search tree, isn't it? And how we have added the tree after comparing it with the root node, or we can say that after searching the location of that new node, then we have inserted it, isn't it? Suppose now in this node I want to add another node that is 20. So what is the process of inserting a new node? We have to compare that node with the root node, and then we can search the proper location for that new node. Okay, so from where you can start the comparison process? From the root node. So here 20 is the root node, right? Sorry, 40 is the root node. So 20 is less than 40, that means we can add it in the left subtree. But this root node 40 has already a left child, that is 33. Now compare it with 33 again. So 20, is it less than 33?
Yes, ma'am.
Yes, then we can add it as a left child of 33. But 33 already has a left child, that is 11. So now we can compare 20 with 11 again. So now 20 is greater than 11. That means we can add where? In the left subtree of 11. So for finding out the correct location or position of that new node, how many times we had to compare the node? Just look at this tree. How many nodes are here? 7 nodes, right? For adding these 7 nodes in their appropriate position, how many times we have to actually perform that comparison operation? How we can find it out? At first, we can individually count. We can count the number of comparison for this individual node. The first one is 40, and when we added that node, at that time the tree was empty. That means for adding 40, the number of comparison was 0, isn't it? When we added the first node in this tree, at that time we didn't compare that node. Hello, can you hear me?
Yes, ma'am. You can.
Yeah, okay. So why its number of comparison is 0? Because 40 is the first node of this tree, so that's why we didn't compare it with any other nodes. Now the next node is 60. So after placing it in the tree, how many times we compare it with the other nodes? Only one time. We compared 60 with the root node 40. How many times? One time. So for that node, the number of comparison is 1. Then the next node is 50. So for inserting it in the tree, how many times we perform the comparison operation? Every time we have to start the comparison operation from the root node. So at first we compared 50 with the root node 40. That was our first comparison. After that we compared 50 with another node 60. That means after 2 comparison we added that node in the tree. So for 50 the number of comparison was 2. Okay, now the next node is 33. For this node, we just needed one comparison. We compared 33 with the root node, and then we inserted it in the left subtree. So for 33, number of comparison is 1. Okay, then when the node is 55. So how many times we compare
Three times.
that node? 3 times, very good. At first with 40, then with 60, and then 50. So the number of comparison is 3. Then the next node is 11.
Two times.
2 times. At first we compared it with the root node 40, and then with 33, then we placed it in its correct position. Okay. And the last node was 20, and for adding it in the tree, how many times we compared? 3 times. Okay. So this is the total number of comparison. This is the total number of comparisons that we needed for inserting all those nodes in a binary search tree. So after adding all the numbers 1 plus 2, that is 3, 4, 7, 9 and 12. So the number of comparison is 12. Okay, so this is a way of inserting any node in binary search tree. Okay, so now after inserting it, how we can delete the node? So I'm taking another tree, suppose this one, 38. 38 has two children, 14, 56. 51 node is 8, and another is 23. And 15 has two children, 45, 82. 23 has one left child, and 82 has also a left child. So this is this a binary search tree? Yes, because all these nodes in the left subtree is smaller than 38. Look at this. For 38, the left child is 14, but this is the left subtree. Okay. So for 14, which one is the left subtree? For this node 14, this is the left subtree, but here there is only one node, and all those nodes in left subtree of 14 should be less than that node. Okay, and this is the right subtree, and you can note it, I mean here 23 and 18, these two nodes are greater than 14, and in the right subtree all these nodes are greater than 38. So this is a binary search tree. Okay, so now from this tree, now if we want to delete the node 8, how we can delete it? Delete the node 8. So this is one kind of binary tree. That means the nodes can have 0 child, 1 child or 2 children. Okay, so for deletion there can be 3 cases. One is we can delete a node with 0 child, or we can delete a node with 1 child, or we can delete a node with 2 children. Okay, so now suppose the first case, that is node with 0 child. If we want to delete 8, at first we have to find out, is there any child node of 8? No, that means this is the leaf node. So at that time we can directly delete that node from the tree. Okay, so if a node doesn't have any child, at that time we can delete that node from the tree. So this is our new tree after deleting 8. Okay, but now the second case is when the node has 1 children. Suppose 23. Now we want to delete 23. So how we can delete that node? Because after deleting 23, where we can insert its left child 18?
Right child of
To delete 23. Okay, so after deleting that node, now its left child should be added in the left subtree or right subtree of 14, because 14 is the parent node of 23. So now we have to compare 18 with 14 first. 18, is it less than 14? No, that means it should be added in the right subtree, and in right subtree there is no other node, so we can directly add 18 as the right child of 14. Is that clear how we are deleting a node? After deleting the node, then we can simply add the child node or child of that node where in the left subtree or the right subtree of that node's parent node. Or think about it here, if we want to delete 82, how we can delete it? After deleting 82, then add its child node where in its parent node. So 56 is the parent of 82, and now compare 70 with 56. 70 is greater than 56, so we can add 70 in the right subtree of 56. So here we can add 70. Okay. Now the next case is when the node has 2 children. Okay, so when the node has 2 children, suppose this one, 56. So how we can delete this node, 56? Look at this node. 56 has 2 subtree. One is this is the left subtree and this is the right subtree. And in the left subtree there is only one node 45. But in the right subtree there are how many nodes? Two nodes. Okay. So here when we are going to delete a node with two children, then we can select a node from, or we can select the in order predecessor of that node, or in order successor. Okay, so what is predecessor and what is successor? Suppose 20 is the parent node and 15 and 25 are its child node, right? So here from 20 we have created two branches to 15 and 25. That means after we have taken this parent node, then we can create some other child node. So here 20 is the predecessor of 15 and 25, but 15 and 25 are successors of 20, isn't it? Hello.
Yes,
Yes, ma'am.
Which one is predecessor here? 20 is the predecessor and 15 and 25 are successors. But here in deletion of a node with two children, we're going to follow this sequence: in order predecessor or in order successor. So what is in order sequence? At first we can take the left child, then the root node, and then the right child. So for this tree, how we can traverse this tree in this method, in order, by using in order traversal method. At first we will take 15 and then the root node 20 and then the right child of 20. Okay, so now here 20 is the parent node, isn't it? 20 has two children, but in this in order sequence 20 is placed in the middle of these two children. 20 is placed between 15 and 25. So 15 is a node which is taken before 20, and here 25 is placed actually after 20. That's why in order sequence 15 is the predecessor of 20 and this right child is the successor node of 20. Is that clear? This is our in order sequence, and the position of 15 we have taken it before the root node. That's why it is the predecessor of root node, and the right child is the successor of this root node. Now here in this tree we want to delete the node with two children. One child is 45 and this is another right child is 82. This is the right subtree. So now if we take the in order predecessor, okay, so now I'm taking some nodes here. Suppose there are some other nodes, 40 and this is 48. So 40 is smaller than 45 and 48 is greater than 45. And all these two nodes should be greater than the root node 38 because it is binary search tree. So now for 56, this is the left subtree and this is the right subtree. And in this left subtree, there are three nodes. So now if we are going to use this one, we are going to take an in order predecessor. Then among those three nodes, which one should be taken?
48.
Why 48? Because this is the largest node in this left subtree. Look at this. We are going to replace a root node by its in order predecessor. And the root node, how we can choose a root node? In a way that its left subtree, all the nodes in the left subtree should be less than that root node, and the right subtree, all the nodes should be greater than that node. So here from the left subtree, we have to choose the largest node, that is 48. Now we can replace this 56 by 48. Okay, and another one is by taking in order successor. Successor means take a node from the right subtree. So this is the right subtree. Now which one we should choose? The smallest value. The node with smallest value should be chosen. So here 82 and 70, which one has a lower value? Obviously 70. So replace 56 by 70. Okay, so after replacing each node, So after replacing this root node by 48 or by 70, then we have to delete it here. Is that clear how we are replacing the root node? It's Is it clear? There are two ways. One is take in order predecessor or take in order successor. And from where we are taking this predecessor and successor, from this in order sequence. In order sequence, the left all the nodes in this left subtree will be considered as the predecessor node of the root node, and all the nodes in the right subtree are actually successor node of the root node. So from the left subtree, choose the highest one. From the right subtree, choose the lowest node. So in this way, we can delete the node from the tree. So any confusion?
No, ma'am.
No. Okay. So that means now we know how to insert nodes in binary search tree or how to delete the nodes in binary search tree. So we can perform another operation, that is searching. So I'm taking the same tree, 38, 14, 56, 8, 23, 45, 82, 18, and 17. Okay, so this is the tree. And now if we want to find out 23, we want to search the location of 23. So this is a binary tree, right? And this tree can be represented by using array or linked list. Okay, and is this a binary tree? Yes, because the nodes have 0, 1, or 2 children. So if we want to store them in an array, so how we can maintain the ordering or how we can assign the location to those nodes. What is the number? What is the index of the first node? 0, right? And for this level, for level 1, the numbers, the index will be 1 and 2. And here the number indexes are 3, 4, 5, 6. And this is can we write 7 here? Can you write 7?
Yes, ma'am.
Yes, so its number is 7 and this one is 8. Okay, so now we are storing the data from this tree in an array. The locations are 0, 1, 2, 3, 4, 5, 6, 7, and the last one is 8. So at first the root node will be stored 38, and then 14, 56, 8, 23, 45, 82, 18, and the last node is 70. Okay, so this is our tree. Now we want to find out the node 23. So we know that for searching a data from an array, we can use two methods. One is linear search and another is binary search, isn't it? So which method should be followed? Which one we should follow here? The linear search or binary search algorithm? Linear search, that means we can search the data element sequentially. We have to start from the first memory location, then we have to search the data element sequentially, isn't it? At first we'll search it in the first memory location 0, then in 1, 2, 3, 4, 5 until we get the data. That is linear search. And what is binary search? If we know the lower bound and upper bound of the array, then we can find out the mid value, and then every time we can compare the data item with the mid value. If the data item is greater than mid value, then we can change the value of lower bound. But if the data element is smaller than the mid element, then we can change the value of the upper bound. That was binary search, isn't it?
Yes, ma'am.
Yes, ma'am.
So, and we all know the complexity of linear search and binary search algorithm. For linear search, the time complexity is order of n, and for binary search, it's order of log n. Why? Because every time we are reducing the array size into half, we are dividing the array into two half, right? Suppose here we want to search which element 23 and its location is 4. The lower bound equals to 0 and upper bound equals to 8. So what is the mid value? Mid equals to 0 plus 8 divided by 2. So here mid equals to lower bound plus upper bound divided by 2. So mid equals to 4. Okay, so here 23 is the mid value. So now if we compare that data, if we write mid, suppose the name of the array is A. So mid A equals to items. At that time we can stop the searching process because we got our desired data. So after that it will return the location. So location equals to mid, isn't it? That is binary search algorithm. Or suppose we are searching for the data item 56. So at that time here mid not equals to item, right? Then we have to find out whether that data is greater than or smaller than 56 or not. But the array we have taken is not a sorted array. So how we can perform a binary search algorithm? Is it possible to conduct a binary search process in unsorted array? No. Isn't it? Hello. Can you hear me?
Yes.
Yes, ma'am. We can hear.
Can we perform a binary search operation here? Is it possible?
No, ma'am.
It's not possible because here 56 is greater than the mid value, but it's where we have inserted it in the left side of the array. So how we can use this method? Is it possible? No. Right? So from this tree, how we can search that item 23? How we can search it?
Ma'am, linear search.
Linear search.
No, the answer is obviously binary. We are going to use binary search method, but forget about the array now. Just look at the tree. Why we're going to use the binary search method? Because every time we are going to compare that data with the root node. After that, we can divide that process, that searching process, into two halves. If 23, if the item is less than the root node, then we will search it in the left subtree, not in the right subtree. So in this way, we're dividing the tree into two halves. That means we are using the binary search process, isn't it? Obviously, we will use binary search algorithm here. So here, the item is 23 and we want to find that item in this tree. So at first, compare it with the root node. 23 is smaller than 38. So now, find that data in left subtree. So now we can ignore the right subtree. In this way, we are reducing the size of the tree, or size of the array. Okay, so now the next node is 14. So 23, is it smaller than 14? No, that means we will not search it in the left subtree of 14. Okay, so 14 is smaller than 23. That means we will find it in the right subtree of 14. Okay, and in which location we found that data? 23 is the right child of 14 and its position is 4. Isn't it?
Yes, ma'am. Index 4.
Its index is 4. So in this way, we can perform binary search process in the tree. Okay, so now what about the array? If we want to represent this binary search tree into array, at first we have to traverse this tree using in-order traversal method. Why in-order traversal method? Because in binary search tree, if we apply in-order traversal method, then the sequence will be arranged in ascending order all the time. Okay, so now apply in-order traversal method. In order, that means take the left child first and then the root child, after that the right child. So here, which node will be taken first? 8, right? At first, take the left child, that is 8, and then take the root node, that is 14. After taking the root node, now take the right child. So 23 is, it's a parent node, so we can't take it. At first, take its left child. So 18 is the left child of 23. This in order sequence. After taking the left child, now we'll take the root node 23. 23. Okay, so after traversing the left subtree, now take the root node. So 38 is the root node. So this is the right subtree. Which node will be taken first? 45. After 45, take its parent node, that is 56, and then its right child. So 82 is a parent node, so at first take its left child, so 70, and then the node is 82. So look at the sequence now. All these nodes are arranged in ascending order: 8, 14, 18, 23, 38, 45, 56, 70, 82. Now, if we arrange them, if we store them in an array, so its index will be 0, 1, 2, 3, 4, 5, 6, 7, 8. So now we can apply the binary search algorithm here, binary search process here, right? And another thing, suppose we want to find out which one is the parent node of 23, or we want to know for 14 which one is the left child or which one is the right child. How we can find it out from this sequence, from this array? 14 is a parent node. Now we want to know in which index we can find out the left child of that node 14 and the right child of 14. Because in this array we didn't maintain the ordering of the tree. In this tree, if the index of 14 is 1, its left child index is 3 and right child index is 4. Right?
Yes, ma'am.
Okay, so now look at the tree. Sorry, look at the array. Now in this array, it's 18 or 8.
18.
18.
18. Yes, ma'am.
Okay. So now in this tree, if the root node is placed in which position, the index of the root node is 1 and its left child is 8, which index is 3, and its right child index is 4. Right, so by using this index we can easily find out the child node of a parent node. But what about this array representation? Here the index value of 14 is 1, but the index of its left child is not 3, isn't it? So how we can find out its the index of its left child node and right child node? Hello.
Yes, ma'am.
Two arrays are given. This is one array where you cannot apply the binary search, but this is another array and we got it after in order traversal method. And in this array, this is a sorted array, so we can apply the binary search process for finding out the location. But now if we want to find out the child node or the parent node of any particular node, which array we should use? This one, the sorted array, or this one? Obviously the unsorted array, because here look at this, the index of 14 is 1, right? So if we want to find out its left child, then we can use this formula 2k for finding out the left node, and for right node we can use 2k plus 1. Hello?
Yes, ma'am.
Okay. So let me draw the tree again. 38, 14, 56, 23, 45, 82, 18, 70. Okay. So now this is a binary search tree. Okay, or forget about the last level. So now this is actually a full binary tree. Right. So in full binary tree, each level has how many nodes? 2 to the power L number of nodes. So now if we store them in an array, okay, how many nodes are here? 7 nodes. And their index values are 0 for 38, and for 14 it's 1. For 56 the index value is 2. And for 18, sorry, 8, 3. Okay, so now we want to find out the left child of 14. Okay, it's left child. What is the index of its left child and index of the right child? Okay, so here if we add the index here 0, 1, 2, 3, 4, 5, 6. So 8 is the left child of 14 and 23 is the right child of 14, isn't it? So now look at the array. Here the index of 14 is 1 and for 8 and 23 the index is 3 and 4. So from this array how we can find out, suppose we don't know about the tree, we don't know about the tree structure. So how we can find out the left child or right child of a node? If we use this equation 2k plus 1 and or 2k and 2k plus 1. So what is the value of k for 14? The value is 1. So 2 into 1, that is 2. So is it the position of its left child?
No, ma'am.
Is it the position of left child? Hello? I don't know why you're not concentrating.
No, ma'am.
It's not, isn't it? So how we can create an equation for finding out their child? For 14, the left child is 8 and the right child is 23. So if we use the equation 2k plus 1 and another is 2k plus 2, at that time, is it possible to find out their child node? Yes, so if we use this equation 2k plus 1, 2k plus 2, suppose for 14, here k equals to, the index of 14 is 1. So 2 into 1 equals to 2, 2 plus 3 equals to 2 plus 1 equals to 3. And in this index 3, when index equals to 3, that will get the data 8. And 8 is the left child of 14. And if we use this equation 2k plus 2, what is the value of k? K equals to 1, so 2 into 1 equals to 2, 2 plus 2 equals to 4. So when index equals to 4, the data is 23. That means 23 is the right child of 14. So in a tree, if we want to find out the left child or right child of any node, we can use this equation 2k plus 1 for finding the left child and 2k plus 2 for the right child. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, so now the next topic is binary search tree traversal. So just like the binary tree, you can use tree traversal method in order, pre-order and post-order traversal. Okay, so here, if we apply the pre-order traversal method, then what will be the sequence? I think you can do it by yourself. Can you do it? What will be the sequence of in order traversal? In order, that means at first take the left child and then the root node and then the right child. That is in order. And for pre-order, the sequence will be root, left, and right. And the last one is post order. So the sequence is left, right, root. Okay. So the first one is in order sequence, right? So which node will be taken first?
8 or
Right. So at first take the left child 8 and then the root
14.
14 is the root of 8. So take 14 and then the right child is 23. So here it is 23. So after traversing the left subtree, then take the root node 38 and in right subtree at first take the left child 45, then the root node 56 and then the right child 82. So this is the sequence of in order traversal method. And the next one is pre-order. Take the root node first and then the left child, after that the right child. So here 38 is the root node, so we can take that node first. Then again 14 is another root node, so take it. And then the left child of 14 is 8 and it's a leaf node, so take 8. Then the right child is 23. Okay, so after traversing the root node and the left subtree of that root node, now traverse the right subtree. Okay, so at first we'll take the root node, that is 56, and then the left child 45, and the last one is 82. Okay, and the last one is post order sequence. So here at first we'll take the left child 8, then the right child 23, then the root node is 14, and in the right subtree first take the left child 45, then the right child 82, then root node is 56. Okay, then the next one will be the root of the tree, that is 38. Is it clear?
Yes, ma'am.
Yes, ma'am.
So now suppose the in order or pre-order sequence is given. So can you create the binary search tree? Only the pre-order sequence is given. So here the nodes are 24, 45, 21, 36, 78, 59, 12, 60. Okay, so these are the node. So how we can now create the tree? This is pre-order sequence, right? That means the first node is always the root node. Okay, so from this sequence, can we create a unique binary search tree? Is it possible? From one sequence, can we create a unique binary search tree? We know that it's not possible in binary tree, because in binary tree we are not, we usually don't concern with this value of the nodes, but in binary search tree we every time we compare a new node with the root node, then we place it in the tree, right? That means in binary search tree, if only one sequence is given, we can create a unique binary search tree. Okay, so the first node is 24. That means this is the root node of the tree. Now the next node is 45. So compare it with the root node. 45 is greater than 24. So it should be added in the right subtree. So 45 is the left child of 24. Now the next node is 21. Is it greater than 24? No. It's less than 24, so we can add it in the left subtree. So 21 is the left child of 24. Now the next node is 36. Compare it with the root of the tree 24. So 36 is greater than 24. So we can add it in the right subtree. But 36 is not greater than 45. So where we can add it?
On the left.
Very good. In the left subtree. So 36 is the left child of 45. Then the next node is 78. So compare 78 with the root node first. 78 is greater than 24. So we have to add it in the right subtree. Then compare it with this node 45. 78 is greater than 45. So we can add it in the right subtree of 45. So 78 is the right child of 45. Now the next node is 59. Is it less than 24? No. So we can add it in the right subtree. So again compare it with 45. 59 is greater than 45. So we have to add it in the right subtree. So in the right subtree there is a node 78. So again compare that node with 78. 59 is smaller than 78. So this is the left child of 78. Okay. Now the next node is 12. Is it smaller than 24? Yes. So add it in the left subtree. And that node 12 is also smaller than 21. So 12 is the left child of 21. Now the last node 60. Is it greater than 24? Yes. And it's also greater than 45. 60 is greater than 45. And here 78 is the right child. So again compare it with 60. 60 is less than 78. But 70 has a child that is 59. Okay. So why will add 60?
On the right of 78.
After comparing it with 78, now we can see that 60 is smaller than 78. So go to the left subtree. In the left subtree, there is another node 59, and 60 is greater than 59. That means it will be the right child of 59. Okay, so in binary search tree, when one sequence is given, we can create a unique binary tree. Okay, but if you want, we can use the method that we applied in binary tree. In binary tree, we use two sequences. One is pre-order or post-order sequence, and another is in-order sequence. So in binary search tree, you can create the in-order sequence. How? By arranging the nodes in ascending order. So here 12 is the smallest node. So in order sequence, the nodes will be 12, then 24, after that 36, and then 45, 59, clear? Hello.
Yes, ma'am.
Yeah, so this is the in-order sequence of the tree. Now you can apply the previous method, that is from the pre-order sequence you can take the root node. 24 is the root node. Okay, then we can identify that node in in-order sequence. So this is, okay, so there is actually another node 21. So this is the position of the root node. Then we can divide this sequence into two halves. So here 12, 21, it will be added in the left subtree, and all these nodes will be added in the right subtree. Okay, so there are two nodes in the left subtree, 12 and 21. So which one will be the left child of 24? The node which is closest to the previous root node. Okay, so in pre-order sequence after 24, the node is
21.
which one?
21.
21. So we'll take 21. So if now 21 is a new root node, again we can divide the sequence. One is, so there is only one node, that is 12. So that 12 will be added in the left subtree of 21. Okay, so in the right subtree there are 5 nodes. So which one appeared first? Obviously 45. There are 5 nodes, 36, 45, 59, 70, 78. But among those 5 nodes, we have taken which one in the pre-order sequence? 45, right? So 45 is the right child of 24. Now this is the root node. Okay, so again divide the sequence into two halves. So in left side there will be only one node. So 36 is the left child of 45, and in the right subtree there are three nodes. Again find out the next root node from the pre-ordered sequence. So which one is the new root node now? 78. Isn't it? Which one we have taken first? Obviously 78. After that the next node is 59 and then 60. So 78 is the new root node now. So after taking 70, now again identify its position in the order sequence. So this is the root node, and before the root node there are two nodes 59 and 60 which will be added in the left subtree. But which one should be added first? 59. So 59 is the left child of 78. Okay, so this is the new root node 59, and there is one node after 59. So 60 will be added in the right subtree of 59. So 60 is the right child of 59. So here actually we are applying the same methods, isn't it? But one difference between binary tree and binary search tree is here, if one sequence is given, you can easily create the tree. Why it's possible? Because all the nodes in the left subtree should be, their values should be less than the root node. Yeah, and in the right subtree, all the nodes are actually higher. Their values are higher than the root node. Okay, so in the next class we'll start another tree, that is AVL tree. Okay, so if you have